Now we will see the inner functionings of least mean square algorithm. We will start off with a very simple problem. So we have a signal y, which is multiplication between a value x and a coefficient called true weight. This true weight is not known, and through adaptive filtering, we'll try to find out the true value of this true weight. So let's get started. So let's generate the x-axis first. So x-axis is linearly spaced numbers between 0 to 10, and let's say there are thousands of them. And let's say the true weight is 2. So let's generate the true signal. The true signal is true weight multiplied by x. And a number of samples is nothing, because we'll be using this again and again. So I'm just initializing a variable called L, and this will be nothing but n is equal to 1000, because 1000 is the number of samples. So we have generated now the true signal, and we will now generate the mean square error surface for the purpose of plotting. So to generate that mean square error plot, we will go through a range of weights. The weights will start from -5 to 9, and as you know that 2 is in between -5 and 9. So let's generate this weight estimate range. Let's call it weight estimate, and again my weights are varying from -5 to 9, and how many number of weights? N number of weights. So weights are as long as the number of samples in the signal. And now we will initialize a array. So now we have 1000 weights. For each weight we will have a mean square error. So to save that error, I'm going to initialize a list. Let's call it error history, and that error history is just an empty list. And now we will initialize a for loop to go through all these weights and then calculate MSE and then save that mean square error in this list. So the for loop for that is, so for each weight in this list, in this array weight estimate, we are going to predict the signal. So my prediction for the weight is nothing but the current weight in the loop multiplied by the x-axis. So this is what this weight is. This weight is in the range here, and x has come from here. So this is what is going to give me the predicted signal. Now we calculate the error. Let's say error is going to be, it's very simple, whatever is my true signal, original signal, and prediction. The difference between my signal and my prediction is my error. What is my error square or square error? It is nothing but square of this error, and then I calculate mean square error, and mean square error is nothing but mean of the error square. So this is what is my mean square error. So once I've calculated it for the current weight, this whole loop is going to go through and fetch all the weights between the range of -5 to 9. So now once I've calculated this, I save it in this list that I initiated. So that will be error history, append, and to this list I'm going to append the mean square error. So at this point, let me plot the true signal and the error surface, mean square error surface that we have generated. For this, I have initialized the plotting code, and let me just run it. So here we are. So this first plot is that of true signal. So if you remember, our x is varying from 0 to 10 here, 0 to 10, and the true weight is 2. So 2 into this xs is going to generate the y signal. So this is what it is showing here. So for the value 10, I should get output 20 because my slope is 2. For 2, I should get 4, and so on and so forth. So my true signal is generated perfectly fine. And then for my weights, which are in the range of -5 to 9, here, -5 to 9, I've calculated mean square error for all these weights. So if you see, I'm starting from -5 going up to 9, and for each weight in this range, there's a mean square error which is depicted by this parabola. The y-axis is mean square, the x-axis is the weight, and as you can clearly see that if the weight is 2, which is the true weight, the mean square error converges to 0. So we have successfully completed these two plots. Now we will implement the least mean square filter to estimate the correct weight or the correct prediction for the true weight, which is 2. So let's build up that logic. So now I will implement the LMS adaptive filter to predict the true weight. So let's start with a random weight, and that random weight is anywhere between -5 to 9. So I'm going to pick one of these weights, and how I will do it is through a function called random.choice, and that random.choice will pick up any one number from the list that we had initialized above, and I just need one number for that. So this is what is my initial weight. I will also define my learning rate, mu parameter, My learning rate is, let's say, 0.001. So I'm also going to initialize some placeholders to keep track of all the weight updates, record of all the weights and all the mean square errors while the LMS is trying to converge to the right solution. So let me initialize a list called weight record. This is just an empty list, and I will also keep track of all my errors. So I will generate an empty list called mean square error record. And once the error have converged to a reasonable limit, then I should stop adapting my filter. So let's define a parameter called error tolerance, and that is let's say 0.01. If the error converges to 0.01 or lesser, my LMS filter should stop iterations. Let's say the current error is 1, and let's say how many iterations it takes for me to converge to the error tolerance. So to keep track of number of iterations, I will initialize a variable called number of iterations and let it be 0. And now I would like to see what weight has been picked up by this random function. So I will initialize, I will just print this number. So initial weight, I'm just extracting the first number from the list, and I'm just printing that out to see what initial weight has been predicted. So let me just run the code. And so my initial weight that has been picked is 6.8. So 6.8 is somewhere around here. And we will start from here, and hopefully if everything goes well, my weight will start converging towards 2, because 2 is the true weight. And we'll use LMS algorithm to do that. So so far so good. Now we will implement the LMS algorithm. So I'm going to initiate a while loop. So the logic of the while loop is that if my current error, which is at 1 now, if it ever becomes lower than the error tolerance, then I should exit this while loop. Basically, I should stop adapting my, or I should stop changing my filter coefficient at that point of time. So let's see. So I have, so let me make a prediction first. I have initial weight right now. So using that weight, let me make my first prediction. So that will be nothing but my initial weight, which has been randomly picked up, multiplied by the x-axis. So this is going to give me my first prediction. And then I calculate my prediction error, which is going to be quite straightforward. Essentially, it is the true signal minus my predicted signal. And then I'm going to calculate the mean square error for this. So mean square error will be MSC. Let's say this is nothing but mean and square of this error that we have calculated earlier. So this is mean square error. And then I'm going to save this initial weight. Right now I've not saved it, I've just printed it. So I'm going to save this by, if you remember, I had initialized these two empty lists, one to keep track of weights and the other to keep track of mean square errors. So now I'm going to use this weight record, and I'm going to append this initial weight there. And also I have calculated this error. I want to save it now for the purpose of plotting. So I'm going to save it in the list that I have. Okay, so far so good. So we have calculated the weights. We have not calculated the weights. We picked up a weight randomly, and then we have calculated the errors and mean square errors associated with it. Now we will implement the weight update rule based on the LMS algorithm. So for that we have to, if you remember, we have to calculate the gradient. Let's call a variable called gradient. And if you recall, this is nothing but -2 multiplied by mu, or the learning rate, multiplied by the prediction error and the signal input to the filter. So this is what is going to give me my gradient. And once the gradient has been obtained, I'm going to update my weight. So my new weight will be my initial weight minus the gradient. And then we are going to prepare for the next iteration. So now my weight has got updated here. Let me just correct it. And now I'm going to prepare the loop for the next iteration. So my initial weight will now become my new weight. That is, the weight has got updated. And my new error. So currently I started off with this error, current error. Now this will also get updated because I have calculated the new error, mean square error. So this will be my current error is updated by my mean square error, and I'm going to increment my iteration counter. by 1. All right, so that's it. This is what is the least mean square algorithm is all about. The heart of the algorithm is this gradient calculation and the weight update part that has been described earlier. And rest are all just print statements and plotting statements. So I'm just going to activate everything now and run this code and hope that this runs perfectly. So here we are, brilliant. So if you see, we started with the initial weight of 8.3. So you can see it here. This is that weight 8.3, and you recall our true weight is 2. So by the end of all these iterations, I should converge to 2. So once I start my LMS algorithm, LMS filter, and start moving towards, so remember this is zero gradient, the slope at this point is 0, and at this point slopes are positive. So the LMS algorithm is trying to find the gradient where the slope becomes 0, and that is the point which is going to give you the true weight. So it starts with 8.397, then it keeps going down with each iteration in the while loop until the error converges to 0.01. If you remember, we had defined a tolerance here. And once that is achieved, the while loop exits. When it exits, the final predicted weight is 2.017, which is very close to the true weight of 2. And it has taken us 87 iterations to reach here. Now, once we take this weight, obviously we plot the predicted signal. And if you can see here, in this plot, the blue is the true signal and the dashed orange line is the predicted signal, and they are overlapping with each other almost, because the true weight is very, very close to the predicted weight. So definitely LMS algorithm works. Now, a couple of things that you can see here is that you can play around with the learning parameter. So if the learning parameter is large, then it takes lesser number of jumps. You see, only in 7 iterations it reached here, and it's pretty close to the true weight. So the smaller the learning rate, it will take more time to converge, but at the same time the filter will be more stable. But if you choose a very high value, the filter might become unstable, though it will converge. It will try to converge. For example, let's just say that my learning rate is 0.1 and my error requirements are this. So you can see here my filter has failed to converge. So we have to choose the learning rate appropriately. In the next example, we'll take a sine signal, a noisy sine signal, and we'll try to filter that out through the adapter filter.